Hi everybody, welcome back to grade 12U Physics. So if you remember last time we finished up our energy ideas, and I told you that we'd be looking at something a little more in general later on, and that something is going to be momentum. And you can probably see the reason we need this if we take a look back and see the issues with some of our methods for solving problems before. So the first one we got, you actually were introduced to it in grade 11, is this idea of kinematics. And the one thing, again, that I stress, and hopefully, again, this is something that sticks in your mind, kinematics does not work. Our understanding of kinematics and our big 5 or 5.5 kinematic equations only work under constant acceleration. But the good thing kinematics does for us is that it gives us actually vector information. So not just size of things, but direction as well. And so to try and get away from this idea of constant acceleration, we looked at this idea of energy. And energy is actually conserved in all interactions. But the only problem with energy is that it only gives us scalar information. If you remember, we never dealt with vectors with energy because they don't actually have vectors involved. They're only scalars. You might notice I have a little asterisk here. And you remember maybe from grade 11 that we have actually mass-energy interactions. But that's something that's a little beyond just where we want to be right now. So right now, let's just say that energy is great. It's more useful sometimes in kinematics, but it only gives us scalar information. And the problem is then if we want to use vectors, we have to go to kinematics, but it's only useful under constant acceleration. So what on earth could we possibly do? Well, hopefully you can gather from the title of what we're doing today, the solution will be momentum. And momentum is one of those quantities that's kind of harder to define. It makes a lot more sense once we get into the math and you get used to this idea, kind of like energy did in grade 11. We calculated kinetic energy, potential energy, but it was kind of difficult to really understand what it was. And unfortunately, momentum's the same way. So I'm going to try my best now to give you an idea of what momentum is, but bear with me for a couple days, and you should get a better understanding of what momentum is as we work through this unit. But again, to give you a bit of a primer, let's consider these two situations. So if I have a basketball and I roll it towards you at a pretty leisurely 2 meters a second, you could easily stop that. It wouldn't be an issue for you. But if I take a car and I roll it towards you at the same 2 meters a second, hopefully you would not try to stop that. You get the heck out of the way. And because that one would be much more difficult to stop than the basketball. And B, you can easily toss or catch an apple that I tossed to you. So if I toss an apple to you gently across the room, you should be able to catch it, no problem. But if I whip it at you, it's going to hurt. And even if you catch it in your hands, it's probably going to sting a little bit. And that's because in each case, A and B, the momentum of these objects is different. The one way I've kind of heard momentum described is the ability of this thing to keep moving. So, or how difficult it is to stop. So if you have more momentum, it's harder to stop, and less momentum is easier to stop. And so the kind of momentum we're going to focus on in our class is called linear momentum, and it's actually just the product of the mass and its velocity. So the two things that are going to make an object more or less difficult to stop are its mass and its velocity. Just a quick aside over here on the side, that there are lots of other kinds of momentum, but in grade 12, we're pretty much exclusively going to deal with linear momentum, so I'm just going to drop the word linear and just call it momentum from now on. So something to keep in the back of your mind. If you go on to physics later on after high school, you'll probably encounter other kinds of momentum like angular momentum and translational momentum, but we're just going to deal with, for this class, linear momentum. All right, so here's our description for linear momentum. And the more details on it, it's a vector quantity, which is nice. Again, we told you the kind of the downfall of energy concerns is that we lose vector information, but now we've got it back again. And the symbol you're going to see given to it by almost everybody is lowercase p. I really don't know why p was chosen. Obviously, m would not be a good choice because of mass, but why p, I don't know. Probably something to do with Latin, but just about everybody that I've ever talked to uses P as its symbol for momentum. And its product is it's given by the product of the mass and the velocity. So just this expression down here. So here's our defining expression for linear momentum or just momentum. And if you carry through the units, you realize that it's actually kilograms meters per second, which is a strange unit. You'd think let's give it another name like momentums. But unfortunately, no one's done that, and so we're stuck with this unit of kilogram meters per second. And the other thing we want to talk about, it'll become important later on, but momentum is a vector, and so we're often going to deal with the components of it, so px and py, which obviously hopefully is just the components in x and y directions, which are just given by the components of the velocity because mass has no direction attached. All right, so there's kind of our idea for momentum. And so let's do a couple simple examples, some plug and chug stuff. So what is the momentum of a 0.400 kilogram baseball traveling at this speed here? So a pretty fast speed, this would be like a fastball being pitched. And I didn't bother looking it up, but this is around the mass of a baseball. And so we want to find the momentum, so of course we know the mass is 0.4 kilograms. We know the velocity is 42.4 meters per second north. All right, and we want the momentum, so that's just P. And again, the only expression we have momentum in it now is P equals mv. So again, I'll leave it to you to plug that in, but I'm getting, when I do this calculation, 17.0. And of course, the unit's kilograms, meters per second, and that's going to be north, the same direction as the velocity. So here's my answer for momentum. So let's do the same thing, but we're going to say that's momentum if we're traveling at half that velocity. So instead of 42.4 meters per second, we're going to be traveling at half of that, so 21.2 meters per second north, and I want to know the momentum. Luckily, momentum is linear with velocity, so I can actually just take half of this, and so I end up getting 8.48 kilogram meters per second north. Again, if you want to follow through, go ahead and you can do that calculation. Pretty straightforward though, and notice this is half of this. And the last question, I'm going to have you actually please pause the video and try this one. So if I have a bowling ball now with this mass and I want it to have this momentum, how fast does it need to be traveling? So again, pause the video, do that calculation quickly for me now, and when you come back, we'll take it up. Okay, so hopefully you've done that question. You've done some rearranging there, and you ended up with an answer of 1.82 meters per second. And that would, of course, if we're looking at velocity, that would be the same direction north. So before we leave this question, let's just look at this for a second here. So we had this baseball, and it had to be traveling at around 20 meters a second to get this momentum, and this bowling ball only had to be traveling around 2. So what the heck can we kind of get from that information? Well, what that really means for us then is that we've increased the mass by about 10 times, so we're decreasing the velocity by about 10 times. And that's something important. Again, if I have a truck that's twice as heavy as a car, it's going to have twice the momentum that the car would at the same speed. So that nice linear proportionality thing, which is always fantastic when we do physics. Okay, so there's that, this idea of momentum, and we say, well, that's fantastic, but it's just a number we're calculating for the heck of it. But now we can actually bring in something kind of cool, this idea of impulse. So impulse is this idea of how do we get the momentum. So if you consider an object at rest, it has no momentum, and then if something pushes it, it's moving. So that means that it has some momentum, because momentum, again, is mv. So during that push, that momentum of that object has changed. So to give it like a more of a concrete example, let's consider a golf ball. So maybe it's sitting on the tee, and you hit it with a golf club, and so then it's going to have an acceleration a. And again, we can see just from, without doing any calculations, the momentum must have changed just because it had no momentum before and now it has some. And so let's go through and see if we can figure out an expression for what's going on. So we'll start with F equals ma, should be very familiar, Newton's second law, which I can write A as delta V over delta T, and I can break change in velocity just up as final minus initial, because again, the change in anything is always final minus initial. Do a little bit of algebraic manipulation, some rearranging, and with this. And if you look at this expression for just a second, you should realize that mvf is just the final momentum, and mvi is just the initial momentum. So we have final momentum minus initial momentum. That's another way to say change momentum. So we end up with this pretty cool expression here, that F delta T equals delta P, or the force times the distance is equal to the change momentum, or sorry, I misspoke there. The force times the time is the change momentum. So this would be the force applied to it, T would be the time that it's applied over, and P would be the momentum. So if I apply a force over a time, I have a change in momentum. And so we're going to call this quantity F delta t, that's going to be given the name impulse. And so when you apply an impulse on an object or you impart an impulse, you're causing a change in momentum. And actually one of the neat little things here, this is a bit of an aside, but if we take a look and rearrange this and write it F equals delta P over delta T, and we remember that F is just, delta P is just M delta V, or I guess more generally I should write then that, oops, there's too many. Sorry here guys. What I should write to be a little more general is then that F equals delta M delta V over delta T. And if we just look at, oh, I've done it again. Oh, sorry guys. First one back, it's been a while. Let me try that one more time. So I can write this as F equals delta mv over delta t. This looks a lot like Newton's second law of F equals ma, because F equals ma, remember A is just delta v over delta t. Holy crud, look at this. There's a connection. And one of those stories that I assume is true, but I don't speak Latin, but this is the original form of Newton's second law, this guy here, or that F equals delta P over delta T. So instead of F equal ma and force equal to mass times acceleration, F is equal to the change in momentum over change in time, which is nice, just devolves down to this. So a couple things before we move on. One, notice that the units for F delta T for impulse are given by Newton seconds. Whoa, that's kind of strange, because the units for momentum, which apparently is equal to impulse, are kilogram meters per second. But if you work it through, and I'm going to actually ask you to do that later on, these two units are equivalent to each other. Newton seconds is the same thing as a kilogram meters per second. And the other thing, that the force we're talking about here is the net force, or sum of all the forces, because our derivation started with F equals ma, which is only true if we're considering all the forces. And the last thing we want to talk about, this quantity impulse, you're often going to see it written as capital J. Again, why is it J? I'm not sure. I'm sure there's some very good reason, but a lot of text, I see the impulse is written as capital J, and so that's what I'll be using if I want to be lazy and not write F delta T. All right, so there's our question. So another quick little check here. So let's consider a situation. A football is being passed to you at 15 meters a second east, and if you catch it correctly, you know, nothing really hurts, and you can run and run away with the ball. If you're not paying attention and it hits you in the head or the chest, it's going to hurt a lot. And why? What sort of things are going on? So again, I'm going to ask you to pause the video here for a minute, think about this question, and try and answer this. And when you come back, we'll look at what I have for an answer. Okay, so welcome back. Hopefully you paused that. And so what I've got is actually looking at the situation. So the football's tossed you at 15 meters a second east. And in both of these cases, I catch it or it hits me, the final velocity for both of these cases are going to be equal to 0. So what that means is momentum before in both of these cases is the same. Momentum afterwards is the same. So the change in momentum in these cases is a constant. It doesn't change. The momentum is the same before and after. So what the heck is going on? Well, if the change in momentum is the same, the impulse you have to impart on the ball is the same. But the difference here is that we're going to either apply a large force over a short time, or our other option is a small force over a large time. And both of these could give you the same impulse. And so the first one where it hurts, that would be the ball hitting you. And the smaller force over a larger time, that would be if you cradle the catch. And if you ever watch a sports player, pretty much no matter what sport they're playing, if they're trying to catch the ball, they're going to cradle it. And what I mean by that is they actually kind of extend the distance of the time they're applying the force by moving back with the ball to try and slow it down slowly. And so you have to apply a small force instead of a large force. But both of them would involve the same change in momentum. So hopefully you got something similar when you thought about it. So let's look at another example, or another sort of idea here. And this has to do with constant force versus variable force. So if we looked at the force that wasn't changing over time, that was pretty simple. We just used the force, and there's our expression for impulse, and then change momentum. But the problem is that forces usually aren't constant. That most time, forces applied to objects change or vary over time. And so we need to be concerned with how do we deal with that. So let's look at a couple of cases here and see if we can come up with a strategy to work through this. So the simplest case is if it's a linear force versus time. That means it changes this way, or just this way, but it's not a curve, it's a straight line. And our expression still holds, but the neat thing here is this expression for impulse of f delta t that I showed you before is just a special case of, let me draw it here with blue on this graph, of this sort of idea, that f delta t would just be the force, which is the distance up here times the time, which is the distance across here. So f delta t, that's the height times the length, that's the area of a triangle or a rectangle. And so we can do that in general and say that the impulse is just the area under the curve. And so give an example with these numbers here. The impulse would be 25 newton seconds north, or 25 kilogram meters per second north. Because they're over this first part, you have a lower force, and over this part, you have a higher force. But overall, this would be your total impulse for the situation. If we look at one that's maybe a little more realistic, because again, straight lines are kind of difficult to get in the real world, we often get things that increase and then decrease at some nice smooth sorts of rates. And so again, it's still the area under the curve, but the problem is it's difficult to calculate. Again, I don't think you get this far in high school calculus anymore, but there is actually a way to calculate the precise area using calculus ideas, and you could ask either Mrs. Hill or Mr. Gilmore to kind of give you an intro into that, but it's something called integration. And we could actually figure out exactly what the impulse is if we knew what sort of shape this curve was. What we also can do is we can just estimate it by counting the squares. So how many squares are fitting under this curve, and there's our impulse. And that would get us a pretty good approximation, and good enough for us right now. But the other option is, if we, the other option here again is that we can look at the same graph, but instead of counting the squares, what we can do is look at the average force. And so this would be a way to kind of ballpark with having to do a graph or counting squares. We can just say the average force applied to this thing, which is going to be this force times this time down here. We're going to get that lovely impulse. So with that in mind, let's do another couple examples here. So the first one here is a golf ball again. It has a mass of 0.125 kilograms, and it's going to accelerate from rest to 35 meters a second west. So from rest to this, and the club is in contact with the ball for this amount of time. And I want the average force applied to the ball. So what we're going to do in this case is again and say F delta T equals delta P. And work through this, and again, just rearrange it then for F. So F in this case will be M delta V over delta T. I'll leave it to you to do a little bit of calculation there and then plug some stuff in. Notice again that we're starting from rest, so our delta V can just be turned into V2. And I'm getting a force then of 97 newtons. And of course, the direction should be west. So that's my answer. Hopefully you're getting something similar. And if not, we can talk about that. And let's do one more here. So let's take a look at throwing a super ball. So again, hopefully you know what a super ball is. You played with them as a kid. They're bouncy balls that are very, very bouncy. And so you're going to throw one at a wall at 10 meters a second east. And this bouncy ball, the super ball, is going to bounce back at 10 meters a second west. So it bounces in and bounces out at the same speed. And I want to know its change of momentum. So again, delta P is equal to mvf minus mvi. Notice I've dropped the vector signs here. Hopefully you're, actually I should probably put them back in for this question since we have directions that are changing. And the one thing we have to do is we have direction changing. So we have our, so we need to pick a direction to be positive and direction to be negative because we have east and west. So let's consider just for the time being here that west is positive, and we're going to do that just so I can say that the final is a positive number. And I go through this and I want to know its change of momentum. And so I'm going to jump to the end here. I'm getting a change of momentum of 2.4 kilograms meters per second. And that direction will be west. So it's traveling from east to west, and our change of momentum in the west because that's the direction the velocity is becoming. If we do the same thing, we have a ball of silly putty now, same mass, but we're going to throw it at the wall and it's going to stick. So instead of bouncing off, it's going to stick, and we'll go through the same sort of idea here. So I'm going to cheat slightly and steal this, put it down here. And what we're going to see here is that our final velocity actually goes to 0. So our final velocity means our final momentum is 0, and so our change of and so what we're going to get here is that the change of momentum is just the negative of the initial momentum. And so what I'm getting for this one, and again, you can verify it, is I'm getting half of the initial momentum, or sorry, the first case momentum is 1.2 kilograms meters per second west. Wow, that's terrible handwriting. And we get that. So the last part of the question here is which ball imparts a larger momentum on the wall or a larger impulse on the wall? That's probably what I should say there. And hopefully, again, you can see that the one that imparts the larger impulse will be the one that has the larger change of momentum, which is the super ball instead of the silly putty ball. And sometimes this is a little confusing for people. But what we can kind of summarize from this is then when a ball or anything bounces off of something, it imparts a larger impulse than something that just sticks to it. And that's going to come up a couple times. And this is something that, again, is a little counterintuitive sometimes to people. So I think that's it for the major topics I wanted to cover here today.